passengers, this is your captain speaking. I hope you're all having a wonderful morning. We will be setting out for New York City in just a few moments.
I'm so excited to go to New York City.
Yeah, there's so many sights to see and places to be.
You know, Tess, even though we've been there before, this is our first time going to New York as a couple.
Aww.
Oh, come on now. We two cut it out. Zayna, Rachel, and I are trying to figure out the bombastic choreo.
I think we should do this.
No, I think we should do this.
David, I've always dreamed of going to Times Square at night. Maybe we could go.
That would be awesome.
As much as I would like to go, I think we could get in some big trouble. But guys, remember when that group of kids got sent to the principal a couple years ago?
I've never been to the principal's office before.
Me neither. I can't ruin my clean record.
Relax.
Is that
Cookies?
We are almost ready for takeoff.
Our chief flight attendant will now explain the rules of the flight.
Hello everybody, I will now be teaching you how to fasten your seatbelt.
Wait, I thought we escaped school. What?
All right, class, you're not escaping just yet. Tess, I'm sorry to invade your dream, but before this plane takes off, you have to learn this math lesson. I have received word from the captain that your plane will be flying at 5 miles high before takeoff and a speed of 400 miles per hour. Let's begin.
On page 181, in Calculus of a Single Variable, Early Transcendental Functions, there is a problem number 67 that deals with the angular rate of change. The problem reads, an airplane flies at an altitude of 5 miles towards a point directly over an observer. Consider theta and x as shown in the figure. There are two parts to this problem. Part A, write theta as a function of x, and part B, which says the speed of the plane is 400 miles per hour. Find d theta dt when x equals 10 miles and x equals 3 miles. As you can see in the diagram, there are two different values given. The plane is flying 5 miles high off the ground and is also x miles away from where the person who is viewing the plane is standing. If you think about this diagram as a right triangle, the 5-mile value will represent the opposite leg, and the x value will represent the adjacent leg in relation to the angle theta. So, in order to write theta as a function, you must use trigonometry. Since you are given the opposite and adjacent legs of the triangle, to solve for theta, you must take inverse tangent times 5, which is the opposite leg, divided by x, which is the adjacent leg. In order to ensure a simpler derivative process, we will change inverse tangent to inverse cotangent, which will also reverse the leg values given. The angle theta and distance x over 5 are both functions of time t. We will now differentiate both sides of the above formula with respect to t. Before we take the derivative, let's not forget the formula for the derivative of inverse cotangent. The derivative of inverse cotangent is equal to negative u prime over 1 plus u squared. After we plug into the formula to take the derivative of inverse cotangent, we will get d theta over dt is equal to negative 1 over 1 plus x over 5 squared times 1 over 5 times dx over dt. As you can see, x over 5 squared is a blob, so you will have to do chain rule on the x over 5 squared, which is where you will generate a 1 over 5. After taking the derivative of the blob and generating 1 over 5, you can put the 1 over 5 in the numerator. As you can see, The newly derived formula is d theta over dt is equal to negative 1/5 all over 1 plus x over 5 squared times dx dt. After taking the derivative, it is time to simplify. We will begin by squaring the quantity x over 5, which will generate x squared over 25. Next, we will perform a simple bow tie to generate one fraction bar in the denominator. We will multiply 25 by 1. After the bow tie, the denominator will read as follows: 25 plus x squared over 25. If you remember back to the beginning of the problem, we were given the information that the airplane is flying at 400 miles per hour towards the viewpoint. Since the plane is flying towards the person, once it is plugged into the formula, it will be plugged in negative because the distance between the plane and the person is getting shorter. To continue simplifying, we will perform Mr. Mantinaos' famous superfast flip to generate one fraction bar. After superfast flipping, we will be left with negative 25 over 5 times 25 plus x squared. Make sure to leave the denominator side by side and do not combine. We can further simplify by simplifying the constant values 25 and 5. And be left with negative 5 over 25 plus x squared. We can further simplify by letting the negative 400 hop on top of the pickup truck and multiply with the negative 5. In its most simplest form, the formula will read d theta over dt is equal to 2000 over 25 plus x squared. When thinking back to the original problem, we are asked to find d theta dt at two different intervals, when x equals 10 miles and when x equals 3 miles. The arrow is pointing at the x, where the two values will be plugged in shortly. When you plug in x equals 10 miles, you will generate an answer of d theta dt equals 16 radians per hour. And when you plug in x equals 3 miles, you will generate an answer of d theta dt equals 58.82 radians per hour.
Now you know all you need to know. You can go back to sleep now, Tess.
All right, everyone, look out your windows. We are almost in the Big Apple.
Prepare for landing.
How was your sleep, Tess?
Good. You'll never guess the dream I just had.
Start spreading the news. I'm leaving today. I want to be a part of it. New York, New York.
Mr. Bombastic, we want some bombastic, romantic, fantastic lover. And then you're a bombastic, very fantastic. Touch me not, says a Mr. Romantic.
2 hours later.
Excuse me, ladies and gentlemen, this is your new captain speaking. Unfortunately, there's been a structural integrity problem due to the velocity that the plane has been going, and we are the A team coming in to land it. Now, my co-captain will give you some instructions.
Please buckle your seatbelts and prepare for landing.
Mr. Bombastic, very fantastic. Touch me on me back, she says I'm Mr. Romantic, very fantastic. Touch me on me back, she says I'm Mr. Smooth. Who's just here? Like a silk. It's me. What's up?